Okay, so last week we covered Bayesian, some Bayesian ideas, right? The idea here is that there's some parameter, okay? But the parameter, unlike the frequentist view, the parameter is not a fixed value. The parameter itself comes from a random distribution, okay? So, I guess we say our data comes from a certain probability distribution. Okay, so for example, we can say our hits for a baseball player come from a Bernoulli distribution with parameter theta, okay? Or I don't know, whatever letter I used last week, okay? So we've got some parameter theta that defines our Bernoulli distribution, right? Okay, and then the key idea here, so what makes it Bayesian is that the parameter, the unknown parameter theta, is a random variable. Okay, it is not a fixed value. It comes from some probability distribution. And those are kind of the key ideas there, okay? Okay, and so we said the posterior distribution is going to be equal, this is how we do it, is the equal to the likelihood times the prior divided by the marginal, which is a constant. Okay, so we have something like the data we observe given, the distribution, the resulting probability distribution. Okay, so this is some posterior probability distribution of theta. Given the data y is equal to the probability of getting the data that we have, if we have some parameter theta, multiplied by the prior distribution of theta, divided by some constant y. Right? And so the beta binomial model says that we can say theta comes from a beta distribution with parameters alpha and beta, and we would say the PDF is some 1 over beta alpha beta theta to the alpha minus 1 and 1 minus theta to the beta minus 1 or something like that. The y's themselves come from a binomial distribution with n and theta. And the posterior is probability of theta given y will come from the beta distribution of alpha plus, I don't know what letter we're going to use, y, number of successes, and beta plus n minus y, okay? Where y is number of successes, and n is the number of trials. Okay, so that's the posterior distribution. And I think this is kind of this is kind of a recap of what we did last week, I think, sort of. And so last week I did the baseball example, right?
Yes.
Okay. So we said, you know, we could say theta is the player's probability of getting a hit. Okay, and we're going to say the prior distribution is going to be beta 81, 219, okay? And this, we'll say 81 and 219 were arbitrarily selected to kind of reflect our kind of knowledge of baseball. Which basically states that nearly all batting averages are between, say, something around 0.200 and 350. Okay. And then, okay. And then, so let's say, you know, we observe a player. Okay. 10 at-bats, 4 hits. Okay. So kind of the current batting average would be 4 over 10. Okay. But that would be the maximum likelihood estimate, but our Bayesian estimate. Okay, so maximum likelihood says kind of our estimate of theta would be 0.4, okay? But we recognize this is you know, too high for like a career batting average estimate. Okay, so that's what we have, and then so instead, so as Bayesians, we say, okay, well, the posterior distribution for theta is that theta will come from beta 85 to 25. Okay, so we have y is 4, n is 10, and then so you have alpha plus y over here and beta plus n minus y. Okay. That's kind of our posterior distribution. We worked through a little bit of the math last week to arrive at this result. All right, and so now the question might be, okay, based on what we have observed for our player, what is the probability that a player will get, I don't know, 3 hits in the next 10 at-bats, okay? All So I'm going to just write this. So our posterior, once again, you don't have to write this again, is theta comes from beta 85 to 25, okay? And then we're going to ask, what is the probability that this player will get, we'll say exactly 3 hits in the next 10 at-bats. Okay. All right, so how do we calculate the probability of getting 3 hits in 10 at-bats, right? The probability of 3 successes in 10 trials. What's that? That would be the binomial distribution, right? So we would use, to answer this, this comes, okay, if we know theta, okay, we can use binomial, right? Because we have n is equal to 10, and the probability is equal to theta, and our x is 3, right? So we would do something like 10 choose 3, and theta raised to the 3rd power, and 1 minus theta raised to the 7th power, right? We need to get 3 hits and 7 misses. Okay, so this would be the answer if we know theta. Okay, so I'm going to call this h of theta. This is our answer. If we know theta. Okay, and so for maximum likelihood estimation, we would just say, okay, well, we had 10 at-bats, 4 of them were hits. Our theta, current maximum likelihood estimate of theta is 0.4, and we're going to just plug that in, and we get an answer, okay? But we know that using 0.4 as an estimate of theta is just, way too optimistic, okay? And so Bayesian statistics says, let's take into account that no one has ever had a career batting average of 400. So let's just be more reasonable about this. And we say, okay, well, what's a more reasonable number? Well, maybe 300, maybe 280, I don't know, okay? And then you say, well, what should I use? Should I use 300? Should I use 280? Okay, 300 being 0.3 and 0.28. And our answer is yes, use them all, okay? Use every possible value, right? And so we would try out every, could it be 270, 272, 275? Sure, we can try any value. We're going to try them all, and we are going to weight them. We're going to say, 0.3 has this probability density in the posterior. 0.28 has this probability. We're going to try them all. Okay, so answer if we know theta. We don't know theta, okay? So we're going to get an expected value. Our expected value of h of theta, okay, that is the expected value of h of theta, okay, over the distribution f, okay, so this is this notation means the expected value of the function h of theta if theta is a random variable with a probability density function PDF f of theta. Okay. So you know, so in this case, f is, what is our f? So for us, f of theta is the beta distribution parameters 85 and 225. Okay, that's our f. Okay, and we want to know what is the expected value of this function h of theta. All right, that is the probability that a player gets 3 hits in 10 at bats. Okay, if our value is theta. Okay, and so this is the integral over basically the domain of theta, okay, of h of theta times f of theta over all, you know, with respect to theta there, okay, given for all possible values of theta, the integral of that. So h of theta is the function, f of theta is the PDF. Okay, and so this is what we're looking at. Okay, so our expected value of the function h of theta is the integral over kind of the domain of theta of h of theta times f of theta d theta. Okay, h of theta is 10 choose 3 theta to the third, 1 minus theta to the 7, and over here f of theta is the beta distribution. What is this? 85, 225 theta to the 84, 1 minus theta to the 224 d theta. Okay, all right, so this is a huge mess, right? So I don't know. Okay, what's 10 choose 3? I can pull at least that out, right? So I can do 10 choose 3 divided by b85 225. I'm sure there's like an easier way to do this, right? And then we can do this. I got theta to the 87. I don't even, this is pointless. Sorry, so 231 d theta. Okay. All right, now how do we do this, right? So, and theta can be anywhere from 0 to 1, technically. Integrate this. All right, so what is this? Can we do this? There's probably a way to do it, okay? But I don't want it, okay? At this point, if somebody said, tell me what this number is, I would just say, okay, I'm gonna go to Wolfram Alpha, I'm gonna type this in and see what it spits out, right? So actually, let's do that. Let's see what Wolfram Alpha spits out here. I don't even know. This is like, am I supposed to expand this out? 1 minus theta to the 231? I don't know. Okay, so, well, what is 10 choose 3? 10 choose 3 is 120. Okay, that's easy. And then what's the beta function? Beta 85, 225. That's some... Oh my goodness. Decimal approximation 2.6, okay, times 10 to the negative 80 power. That is really tiny. Okay. All right. Well, okay, so I'm going to do 120 divided by this times the integral of okay, so I'm going to put an x, right? So I'm going to do x to the 87 times 1 minus x to the 231 dx from 0 to 1. Did I type that in right? I think that looks correct. Okay. All right, Wolfram Alpha, let's see what you got. Definite integral 0.0 0.25824, decimal approximation. Okay, all right. 0.25824. Okay, that's what Wolfram Alpha says. Okay, so Wolfram Alpha says it is approximately what? 0.25824. Okay. Oh, look at this. It gives us the indefinite integral. This is... It keeps going. Oh my goodness. Look at this. Wow.
Thank God we have it.
Huh?
So thank God we have it.
Yeah. Okay. Plus a constant. Okay.
Oh.
Raise x to the 88 over 88. Okay. All right. Well, we don't want to do that, right? Okay. So... All right. Well, okay. Here we're going to do Monte Carlo integration instead. Monte Carlo integration. This says we do this, right? So this is just a I guess Monte Carlo methods in general is basically estimating quantities like this using our computer's ability to generate randomness. Okay, so we're going to we estimate quantities using our computer's ability to generate random values. Okay, and so this is the idea. We're going to say the expected value of h of theta, okay, where theta comes from some distribution f. This is approximately equal to basically the mean of h of theta for if you draw many values of theta from f. So just say, just generate, what this basically says is just generate a ton of theta values, okay, from this distribution f. And when you do that, naturally, the ones that occur more often, like 0.3 and 0.28 or whatever, those will appear a lot in your resulting distribution. Other values like 0.4 and 0.1 and 0.9 or whatever, those will happen very, very, very rarely in your distribution, okay? And so if you see 0.28 show up a lot, okay, and you probably won't get the exact value 0.28, but you know, values around 0.28 will show up a lot, and so they will get averaged in many times here. And other values that show up very rarely will get averaged in, but they're not going to affect it very much because they show up very rarely, right? And that's it, okay? There is a book, Monte Carlo Methods, Introducing Monte Carlo Methods, and it has the formal notation here. Let me see if I Introducing Monte Carlo Methods with R. You can get it for free as long as you're connected to the UCLA VPN. You don't have to read it. Okay, so what do we have? This is what we have, h of x. Okay, I guess they're using h of x times f of x dx. This is what we got. And the estimate is, okay, we're going to call our estimate is this. So okay? All right, so I'll just go ahead and write that's our estimate. This is the Monte Carlo estimate. Is equal to basically the mean sum up through n over h of xj. Okay, where basically xj gets sampled out of some xj is our random. I should use theta to stay consistent. All right, sorry, the book uses x, I'm using theta. Okay, so our random value is drawn from f. Okay, so I hope let's try this out. I hope this works. I didn't do this last week, right?
No.
Okay. Sometimes I confuse myself. So actually many times. All right. Okay. So we're going to. All right. So I'm going to just draw theta. Okay, coming from f. Right. So to generate random values from the beta distribution. Okay. R has a whole bunch of distributions built in, and to get random values, you use R. Okay, pretty much all distributions have maybe this is worth its own slide here. Okay, in R, all distributions have 4 functions. Okay. You've got D blank, P blank, Q blank, and R blank. All right, so like D norm, P norm, Q norm, R norm, okay? Or, you know, D beta, P beta, Q beta, R beta. And the D is density. This is equal to the PDF. P is the cumulative probability. PDF/PMF, okay, is D, okay. Cumulative probability is the CDF. Q is the inverse CDF. Okay, so cumulative probability, basically you plug in any value of x and it outputs something between 0 and 1, right? The cumulative probability between 0 and 1. I don't know. This is your PDF f of x. This is big F of x, which is equal to negative infinity up to x of f of t dt. And then the inverse CDF is the inverse of this. So for the inverse CDF, you plug in any value u between 0 and 1, and it outputs the cumulative probability. And then R is for generation of random values. Okay. So if we're talking if we're talking about the normal distribution, D norm of 0 is around 0.4. Okay, that's on the normal distribution curve. The tallest point, and the density is around 0.4. It's like 1 over square root of pi something something, okay? The p norm of 0 is 0.5, okay? If the cumulative probability at 0 is 50%, okay? Inverse q norm of 0 would be negative infinity, okay? Q norm of 0.5 would give us 0. So the p and the q are inverses of each other, okay? And then r norm will generate random values. In this case, we want to generate random values from the beta distribution, okay? And I'm going to ask for like, I don't know, 1,000,000 of these things, okay? And shape 1 is 85, and shape 2 is 225, all right? And then my h is a function where of, I guess, theta, all right? And this will return, choose, I'm going to just do 120, okay, 120 times theta to the third times 1 minus theta to the, what do I do? To the 7th, okay? Is that all right? And, okay. And so my estimate is going to be the mean of h applied to my 1,000,000 values of theta that I've drawn from the beta distribution. Does that feel okay? And we are hoping that when I run this, I get a value close to 0.25824. Oh, I'm nervous. Okay. Oh, look at that. 0.258243. Okay, that's about as good as I could have hoped for. Okay. And that's it. Okay. So rather than having to do the integral, rather than having to go through all of this work, even just typing this into Wolfram Alpha felt like a bit of work. Okay. You know, rather than having to compute this, we just use a random sample. Here I'm asking for 1,000,000 values drawn from the beta distribution, our posterior distribution. And then we apply our function to it, and then we take the mean of that function applied. Okay? Here, I can try this again. Whoops. And I might get it, I'm going to probably get a slightly different answer. But it still comes out very close, right? 0.2582314, okay? And the true value 0.25824, okay? So 0.25824, 0.25824, 0.25823, okay? So, you know, I would say we're getting pretty good estimates of the unknown quantity, okay? All right, how do we feel about this? So this is Monte Carlo integration here. Okay, so I'm going to go ahead and I'll just, let me actually open this back up. Lecture slides. Fit this right here. Okay, so we get this. Okay, pretty good. All right, so that okay, so that's kind of our first thing, Monte Carlo integration. Says This is it, right? The expected value of some function, h of theta or whatever it is going to be the integral over all values of theta, of h of theta, times the probability distribution. Okay, and this can be estimated using the mean of h of theta, okay, and basically after drawing many values of theta from the desired distribution. All right, okay. So this is great for anytime you're using a conjugate prior situation. This works out really well, okay? Because R will have pretty much all of these distributions built in. It's got like the beta distribution, T distribution, gamma distribution, all of, log normal, inverse, whatever, Wishart and stuff. It's got a whole bunch of distributions built in, and you can do this, right? Okay, but we also run into situations where we don't have some kind of predefined function in R, okay? So after drawing many values of theta from the desired distribution. All right, so here we'll talk about, I'll just write sometimes we need to draw values from a distribution that is not, quote, built in to R, right? So if we're not dealing with a conjugate prior, not some nicely behaved distribution, we might need to draw values from something that's not built into R, okay? So I'm trying to decide how much time I want to devote to all of this, okay? So I teach a class on Monte Carlo methods for the undergrads, and we spend like 10 weeks on the topic, and we cover about like generating all of these things. I'm going to just jump ahead to Markov chain Monte Carlo, okay? So we're going to skip, so you can go in this textbook, you can read the chapter on random variable generation and whatnot. I'm going to just skip ahead to right here, chapter 6, Metropolis Hastings algorithms and stuff. But, so there's topics on random number generation. Okay, and this includes topics like inverse CDF method and rejection sampling, etc. Okay? Not covered in our class. Could be of interest to you. We're actually going to skip over what used to be a very important topic, and that was how do we even generate random numbers on a computer? Because a lot of these things, even these random number generation things, or random variable generation, I guess we always assume we can generate from the random uniform. So random uniform 0, 1, we're always assuming we can generate random values between 0 and 1. And all of those values are equally likely to appear. This is This is a complicated topic, and even gets philosophical. I don't know, right? So if you think about it, a computer is actually not random. It's like the opposite. It's supposed to always behave in a predictable manner. If you give it some instructions, it should always do the same thing, and it does. And so when we talk about generating random numbers on the computer, we have to call these things pseudo-random, because we can, if I give my computer the same starting conditions that you give your computer, we will both generate the same quote-unquote random sequence of numbers. Okay, but if we're generating the same sequence, obviously it's not truly random. And I don't know, there's a bit of a question, are things really random, right? Like if you flip a coin, technically, if you knew the exact force that was applied to the coin and its angular velocity and momentum and all of that, you might be able to predict how it will land. But for our day-to-day, we just treat this as random. So I don't know. There might be randomness at the quantum level. We think there is, but maybe that just means we don't fully get it either. Okay. So anyway, we're not going to bother with that. We're going to just go ahead and jump to MCMC, which stands for Markov chain Monte Carlo. All right. And this is very useful when the distribution that we want to draw values from might not even be fully defined. Okay, so we'll say very useful when the random distribution is not even fully defined. All right, how can that even be the case, right? How can you have a distribution that's not even fully defined? Okay, so which actually is a frequent occurrence in Bayesian stats. Okay, so let's just think back to the Bayesian posterior distribution is equal to the likelihood times the prior divided by the marginal. Okay, what is the marginal? Do you guys remember the marginal? Huh? Yeah, the marginal is it's a constant and is equal to the sum or integral of the numerator across all possible values of theta. Right? So if I say the probability of theta given our data y is equal to the probability of y given theta times the probability of theta divided by the probability of y, we can say the probability of y is equal to the sum of this over all possible values of theta or the integral across all possible values of theta of this. Okay, and this quantity might be very difficult to calculate. Okay, So it is often the case, okay? So we often have the probability of theta given y is proportional to, so that's what this symbol represents. It's kind of an ugly thing. I don't know how to do this. It's like, okay, is proportional to just the numerator. Okay, so we don't know the exact form of this because there's some constant missing here, all right? Because for it to be a PDF, this function needs to integrate to 0. I mean, not integrate to 1, okay, for it to kind of be a PDF. But we don't know what that constant is, okay? So we don't have the PDF of the random distribution fully defined. We just have something that's proportional to it, okay? But but we have the Metropolis algorithm, and the Metropolis-Hastings algorithm works very well in this situation, okay? So Metropolis So, I mean, you can use a Metropolis algorithm even when the distribution is fully defined, but it will still work even if it's not. Even if you're missing this, what we call the normalizing constant, you can still do this. All right. Does this sound good? All right, so this is how it works, okay? Well, I guess before I get into Metropolis, let me just talk a little bit about Markov chains, okay? So a little bit of theory on Markov chains. Have you had any exposure to Markov chains before? A little bit?
Yep.
Okay, and what can you say about Markov chains?
So they are sort of a series of states where in each iteration things are probably moving from one state to another.
Right.
And then so for each state you have a probability of staying in that state, which is, and then probably moving to every other state,
right,
which sums up to 1.
Okay. Yeah. So and right, and the Markov part is that the probability of moving to a new state depends only on the current state. Okay. So yes. So in Markov chains, we build this random sequence of states. Okay. So I guess a chain of states. Okay. So we build a kind of random sequence of states, okay? At each state, okay, or at each point in the chain, random sequence, or this could be thought of as a chain, okay? At each state, we might transition to a different state, or remain at the current state. Okay. And the probability of transitioning to another state depends only on the current state. Right? So I guess you can think of weather in Southern California. And we basically have sunny and something else. Some kind of precipitation or cloudy fire. I don't know. All right. And so, most of the time, it's sunny today, and then, you transition the next day, it's also sunny, and you keep having sunny days, and then every now and then you get something else, and maybe you keep having bad weather for a while, and then it transitions back to sunny. Okay, so I don't know what this is, right? Okay, and so you might so I'll call sunny S, and so you can have, so the sequence could go S, sunny, 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 and then I'm going to call this something else, and maybe you have 2 days of bad weather, and then you have sunny, 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 and then maybe else, sunny. I don't know, this is also possible, right? And basically, if we're looking at this day and we say, what's going to happen next? Okay. What happens next? So, what happens to the next day? The answer is it only depends on this current state. What happened the days before doesn't matter, okay? It doesn't matter that you just had rain yesterday, okay? What's going to happen tomorrow depends only on today. That's kind of this Markov property. The Markov property is also known as the memoryless property because it has no memory of what has happened in the past. What's going to happen next depends only on the now, okay? And that may or may not be a good simulation of reality, but it surely simplifies the math, and it can be reasonable to think of reality like this. Okay, so the Markov property is also known as memorylessness. Is that even a word? Memorylessness. What happens next depends only on the current status, okay? Okay, so we build a transition matrix, okay? This is our transition matrix. We often call this P, okay? The transition matrix P, and this will be now and next. Okay, and so we'll have sun, sunny, and something else. Sunny and something else. Okay, and I don't know. Basically, the rows will sum to 1. And so we'll say if it's sunny, maybe 80% probability it'll be sunny the next day, and 20% probability that it won't be sunny the next day. Okay. And then if it's something other than sunny, okay, maybe there's a 60% probability it'll be sunny the next day, and a 40% probability that it remains in bad weather or something. I don't know. Okay. So this is what we have, and I guess we could label our arrows. I can say this is going to be 0.8, this is 0.2, this is 0.6. I'm sorry, this is 0.4. Wait, something else goes to Sunny. Okay, yeah, no. This is 0.6 and this is 0.4. Okay, that's how it goes. All right, and so a little bit of theory on marker chains. We build a random state. Okay, so this is what we've got, and the idea here is that there's something we call, I don't know, ergodic theory. And the idea here is that if you let a Markov chain run long enough, so the Markov chain is defined by its transition matrix, and if you let it run long enough, then it will reach what we call the stationary distribution, okay? So, so we'll say, you know, a Markov chain is defined by its transition probability. Transition probabilities. And the ergodic theory says if a Markov chain is irreducible and aperiodic. This is like the light version of the theory, okay? There's like more detailed axioms of this. I'm just giving you the light version, okay? So don't try to take this and make some, you're not getting the rigorous version of this, okay? So if a Markov chain is irreducible and aperiodic, then given enough time, it will converge to its stationary distribution, okay? The stationary distribution happens when the states are at equilibrium, okay? So when they're not at equilibrium, if you apply the transition probabilities, things move around, okay? Things will move around. You've got too many of this, and it moves over here, and things move around, okay? When it reaches the stationary distribution, everything's kind of at equilibrium. Yeah, you apply the transition things move, but like individual states might flip and stuff, but the probabilities remain exactly the same. The probabilities are unchanging once you reach the stationary distribution. Okay, we'll converge to a stationary distribution. So the stationary distribution is the kind of probability distribution where the probabilities do not change after applying the transition probabilities. Okay, the probabilities do not change. I'll just say after applying the transition probabilities or matrix. There's a couple terms that I threw in here, irreducible and aperiodic, right? And again, this is the light version. Irreducible basically says you can get to any other state from any other state, okay? That, there, I guess, a path exists between any pair of states. All right, so you can have A, B, C, and D. All right, so I got A, B, C, and D. All right, and if you have this, okay, this is irreducible. Okay, everything doesn't have to be connected, but if you're at C, you can get to B. Okay, go through A first, and then from A to B. Okay, if you're at you know, wherever A, you can get to D. Okay, it takes a couple steps to get there, but you can get there. All right. Not irreducible would be something like you've got A, B, C, and D. Okay, if you've got this, all right. Let's say you have that, okay? This is not irreducible. This is, there's no path. Like if you're at D, you can't get to A, right? Or B, right? So you can, from A you can get to B or C or D, okay? And from B you can get to all the other states. But from C, you can't get back to over here, right? So this is, I guess we would call this reducible. Okay, that's that. Aperiodic. Well, aperiodic basically means not periodic. Periodic means that only certain states can happen at certain intervals. So I guess states can happen at any time. Kind of on a practical level, can happen at, I don't know, any time in the sequence. Practically speaking, basically means if it's possible to go from a state back to itself, it's going to make this chain aperiodic. Okay. Possible to go back to the same state in one turn, right? Like if it can go from sunny to sunny, it's going to be aperiodic, okay? If it's possible to go back to the same state. Okay. There's going to be more if we go to Wikipedia ergodic theory. Ergodic. Maybe I want. Which is the one I want? Irreducibility, Markov chain. In a Markov chain with a finite state space, the state I is said to be ergodic if it is aperiodic and positive recurrent. A state is recurrent if there's non-zero probability of exiting the state. And okay. If all states in an irreducible Markov chain are ergodic, then the chain is said to be ergodic. Okay, so that's a little bit more formal here. Okay. All right. So anyway, all this to say, you've got this thing. It's going to converge to its stationary distribution, given you enough time. So what did I say? Okay. Let me show you an example. All right, so we've got California and we've got New York. All right, and we can talk about sometimes people move from California to New York, sometimes people move from New York to California. And we can think of these as our two, I guess, literal states here. And I don't know, we can make up numbers here, okay? So if you're in California, what's the probability you stay in California? And if you're in California, what's the probability of moving to New York? All right, I don't know. How many people from California move to New York each year? We'll say 5%. I don't know, okay? And how many from New York move to California? More?
Definitely more.
8%. Okay. I don't know. I'm making this up, okay? All right, so we want the stationary distribution, okay? So if this is my matrix P, so my matrix P, I can write as like this, 0.95, 0.05, 0.08, 0.92, okay? And the stationary distribution will be pi. This, I don't know why it's called this, but this is it, okay? And this will be California and New York, all right? So we can start off at half of the people live in California, half of the people live in New York, okay? Oh, I'm sorry, that's the stationary distribution. I'm gonna call this pi California and pi New York, okay? This is what we want, all right? And we'll just say current distribution will be half live in California, half live in New York, okay? And we apply the transition matrix, 0.95, 0.08, 0.05, 0.92, okay? And so we do this, 0.95 times 0.5 plus 0.08 times 0.5. I don't know what that ends up being. 1.03.565 and 0.485, something like that, okay? Basically, some people moved to New York. From California, we had 0.04 went from California to New York, and then 0.025 went from New York to California. So California went from 0.5. Oh wait, did I mess this up? No. I have, it should be swapped away, okay? So, 0.004, right? So 2.5% went from California to New York, but then 4% went from New York to California, and then the other way around, okay? 4% went from New York to California, and 2.5% went back. So New York had a net loss of, I guess, 1.5%. And California had a net gain of, this is 515, okay? Net gain of 1.5%. Okay, and then we can apply the transition matrix again. All right, I can do 0.95 and 0.05 and 0.08 and 0.92, and then and we would get something else. Maybe I'll just have the computer help me out here, okay? So I'll call P the matrix of C, so I have 0.95, 0.05, 0.08, 0.92, and I want 2 rows, and I'm going to say by row is true, all right? Okay, so here's P. All right, and then if I say my distribution D is 0.5 comma 0.5, okay, I can do D times P, all right, and then so my distribution at this point is what I have here, 0.515 and 0.485, okay, and I can take this result and multiply that by the transition matrix P again, and I would get 0.52805 and 0.47195. Okay, and then I can just repeat this over and over again. Oops. All right, and it keeps so we can see people keep moving from California to New York to California, okay? But eventually it will reach some stability here, okay? So we can see at this point it's reaching 0.6153 something, and let me see. Okay, so if I do stationary is going to be 8/13 and 5/13, okay? So eventually it'll reach this stationary distribution, okay? We were getting pretty close, okay? But I would have had to run it for a few bit more iterations, okay? And if I take my stationary distribution and I apply the transition matrix, I get the exact same thing back again, okay? So the stationary distribution doesn't change if I, apply the transition matrix, okay? So the stationary distribution will be 8/13 and 5/13, okay? So if I have 8/13 and 5/13, and I multiply it by 0.95 and 0.05 and 0.08 and 0.92, maybe you can see, all right, so out of the 8/13, 8 times, I would have 8 times 0.95 plus 5 times 0.08 over 13. And then, and if we look at this, this will add back up to 8/13, okay? And then same on the other side, okay? And basically at this point, the amount flowing from California to New York is exactly equal to the amount flowing from New York to California, okay? There's a nice little all right. Okay, so this is California and New York, and so here this is some transition probability, and I don't know, right now you can see there's a big ball of, here I can move like, we can start with equal size balls for California and New York, okay? You got the yellow ball for New York, yellow ball, and the blue ball for California, and you're gonna see some from California move to New York and some from New York move to California, right? I think the probabilities here say 90% stay, so 10% of California will go to New York and 30% of New York will go to California. And what we're gonna see is that some go from California to New York, okay? And with each iteration, New York gets a little bit smaller, okay? And California gets a little bit bigger, but at a certain point, the number that flow from California to New York equals the amount flowing from New York to California, okay? And I can kind of start this off like this, okay, where we've got everyone at New York, okay? So no one's going from California to New York, okay? And here, 30% of New York moves to California and only 10% of California moves to New York. And so it takes a few iterations, but now we've reached kind of this state of equilibrium where now we have basically the same number from California going to New York and New York going to California, okay? And you can start at the other side, okay? You can start with everyone in California, and 10% will go to New York, okay? So that's this much. And then 30% of New York will come to California, and it continues that every time 10% of California goes to New York, okay? And 30% of New York goes to California, but eventually, after enough iterations, it reaches this equilibrium where the amount flowing back and forth is the same for both sides. So that's kind of neat, right? Okay, so that's what we've got here, right? Okay, 7:20. Here, why don't we take a 10-minute break here, and then we're going to take this concept of a Markov chain and develop the Metropolis algorithm, and then we've got this little application that I thought was kind of neat.